All right, today we're pulling back the curtain on a technology that's, well, it's pretty much everywhere, quietly changing how everything works. We're going to dive into the fascinating world of machine learning. I mean, have you ever really stopped to think about it? How does your phone know? Every single day it looks at your inbox and just decides, nope, that's junk. It's incredibly accurate, right? But how? Well, it's definitely not magic. And it's not like some programmer wrote a million different rules for every possible spam email out there. That'd be impossible. The real answer is something way more clever. It's a system that has literally learned how to spot the difference on its own. And that, at its heart, is what machine learning is all about. Instead of giving a computer a super rigid set of instructions, we give it a goal, and then we give it a whole lot of data. The computer then teaches itself to find the patterns and make predictions based on all those examples. It's learning from experience, pretty much just like we do. So, how does this learning actually happen? Well, there are a few main ways. Let's start with the first and most common one, which is called supervised learning. The best way to think about this is like studying for a big test, but you've been given the answer key. You try a problem, you check your answer, and you adjust your thinking for the next one. That's exactly how supervised learning works. We feed the machine a ton of data that's already been correctly labeled. So going back to our spam filter, this means feeding the algorithm thousands of emails that a human has already marked as spam or not spam. Or take a look at this example for movie reviews. We show it the sentence, "I love this movie," and we tell it, hey, that's positive. It sees the input and the correct output over and over and over again. And what's happening under the hood is really cool. After seeing thousands of these examples, the model starts to notice that words like love and amazing show up a lot in positive reviews. And words like dislike and terrible show up in the negative ones. So it starts assigning a kind of sentiment score to all these words to build its own understanding. So here's the crucial part. The model makes a prediction, it checks it against the answer key, and then it measures how wrong it was. In machine learning, that measure of wrongness is called a loss function. The entire goal of the training process is just to tweak and adjust itself relentlessly to get that loss score as close to zero as humanly, or I guess machinely, possible. Okay, that's great if you have an answer key, but what if you don't? What if you just have a giant, messy mountain of data and you want to see what's hiding in it? Well, that brings us to our second approach, unsupervised learning. This time, we don't give the machine any answers. We just hand it a pile of data and basically say, go find something interesting. It's like being a detective. The algorithm has to sift through everything on its own, looking for natural clusters and relationships that a person might never see. And this isn't just for sorting customer data or something abstract like that. Unsupervised learning can solve actual, real-world mysteries. In fact, it helped crack a literary cold case that was almost a century old. So you know the Oz books. The original author, L. Frank Baum, passed away. The publisher hired a new writer, Ruth Plumley Thompson, to continue the series. But the very last book credited to Baum, The Royal Book of Oz, it felt different. For years, dedicated readers suspected Thompson had secretly written. To solve this, researchers turned to data. They took all the Oz books plus other books they knew were written by Baum and Thompson, and they broke them down into tiny chunks. For each chunk, they counted the frequency of simple function words. You know, the little words we all use without thinking, like with, upon, and so. The idea is that these words create a unique, subconscious authorial fingerprint. And this is where the magic happens. They fed all those textual fingerprints to an unsupervised algorithm and told it to find the groups. And look at this. With no labels, the machine found two totally distinct clusters. You can see on one side all of Baum's known work, and on the other, all of Thompson's. The machine found two separate authorial fingerprints all on its own. So, the million-dollar question, where did the mystery book land? The data points from the Royal Book of Oz, you can see them as the little hearts, fall smack dab in the middle of Thompson's cluster. Undeniably, the machine, acting as a literary detective, confirmed what fans had suspected for decades. Okay, so for our third approach, we're shifting gears completely. This isn't about learning from a static pile of data anymore. This is about learning by doing, by interacting with an environment. This is reinforcement learning. Honestly, the best analogy is training a pet. When your dog does something you want, like sitting, it gets a reward, a treat. When it does something you don't want, it gets a penalty, or at least no treat. Over time, through trial and error, it learns which actions lead to the best rewards. A machine learning agent works in the exact same way. It's a constant loop. Step 1, the agent takes an action. Step 2, the environment reacts and gives feedback. Step 3, the agent gets a score, a reward, or a penalty. And step 4, it adjusts its own strategy, always trying to figure out how to get the highest possible score in the future. Now just imagine that simple loop repeating itself, not 10 times, not 1,000 times, but millions, or even billions of times. That's how an AI can go from knowing absolutely nothing to achieving superhuman performance in a complex video game. It's also how we're seeing robots learn to do incredible things like parkour, all through this massive, scaled-up process of trial and error. So we've seen just how powerful these learning methods can be. But, with that kind of power comes some pretty enormous responsibility. And that brings us to a really critical final topic, the ethics of machine learning. Look, if an AI recommends a movie you end up hating, the stakes are pretty low. But what happens when we use these models to decide who gets a loan, who gets a job interview, or who gets parole? The consequences of a mistake or a hidden bias can be absolutely life-altering. We have to make sure these systems are fair, which often means telling the system that certain things, like a person's race, are protected attributes. But here's where it gets really tricky. What does fair actually mean? One popular definition is what's called demographic parity. This says a model is fair if it gives the same outcome to different groups at the same rate. So, for example, the loan approval rate should be the same for every racial group, period. Sounds reasonable, right? But then there's another definition, predictive parity. This says a model is fair if it's equally accurate for all groups. So if the model approves a loan, the chances that the person will actually pay it back should be the same no matter their race. In this case, the focus isn't on equal outcomes, it's on the reliability of the prediction itself. And here is the profound, massive challenge. Researchers have proven mathematically that, except in some very rare cases, you can't have both of these at the same time. These two common-sense, intuitive ideas of fairness are fundamentally at odds. If you build a system to be fair in one way, it will almost certainly be unfair in the other. So as we build these tools that will absolutely shape our future, we're left with a question that isn't technical, it's deeply human. What do we value most? And how do we decide what is truly fair?